So this is the revision section on all of waves. It's quite a long one, as all of these are going to be. So pause it occasionally. And also when you've finished, and if you can, try and watch the PowerPoint in its original form with the animations. They may help. And if they don't, and you don't understand still, come back and listen to it again in a few days. These are resources which aren't going away. Okay, so just some very simple ideas about what different words mean in waves. A crest is the top of a wave, the trough is the bottom, and the distance between the middle and the crest of the trough, that's called the amplitude, the height of the wave. A wavelength is the distance commonly called from peak to peak, but as you see in the diagram, it's any two same points on a wave. And the frequency, measured in hertz, is the number of times it goes up and down in a second, the number of oscillations that pass a point in a second. I should also remind you that wavelength is measured in meters. Okay, two types of waves. Transverse, which oscillate at right angles to the direction of propagation. Light is the principal example of this. And longitudinal waves, which oscillate in the direction of propagation, and sound is the principal example of this. Again, because of the format I'm using here, you don't see the animations, which are much easier on the actual PowerPoint itself, but I haven't yet worked out a way of doing that, but we'll work on it. Anyway, I should say that this is of course not how I hope you will explain the difference in a question. You'll say that transverse waves can be polarized and longitudinal waves can't be polarized because they only have one direction of propagation to start with. Okay, so the wave equation, which is in the logbook, but is worth remembering. The speed of a wave is its frequency times its wavelength. This is such a common piece of advice that there's hardly a question in waves, in some of light, and certainly in most of the nuclear section, which doesn't involve this formula. So definitely worth being familiar with it. Not remembering it, of course, because that's in the logbook, but being familiar with it. So getting on to some actual memory stuff. Diffraction is the wave spreading out. Spreading out. Did I say that? Yeah, spreading out from an edge or a gap. The only other thing to remember about it is that you get better diffraction if you have a wave which is similar to the gap, which actually means that a longer wavelength with decreased frequencies actually diffract better. So sound diffracts better than light, because light's a short wavelength. It doesn't diffract as much as sound. Sound diffracts more because it has usually a longer wavelength. And radio waves, which have a very long wavelength, diffract very well, which is why you can detect radio waves in all sorts of places which seem to have no clear line of sight. So, thought I'd throw this in again. Total Turner reflection seems to come up all the time. An example of optical fibres, the light reflecting on the inside due to it being greater than the critical angle. You have to coat all of the strands in something of a low refractive index, a low N, and this increases the amount of retained light by changing the critical angle. Also, though, if the two strands touch each other, light doesn't leak from one strand into the next. Detection, also another important point. You can detect here infrared, either with an infrared glasses, or as they are called, night vision binoculars, or you can simply use the blackened bulb of a thermometer, which is the third one down here. It's been darkened, and you can see the temperature is higher. It's higher there. It's above the other two, because the infrared is heating up the bulb, being absorbed by the black paint on the bulb. Obviously, you have to leave another bulb, or even two, without the blackened paint to compare the temperature. As for UV light, basically UV light can be detected in a darkened room with a white cloth washed in an optical brightener, which means all white cloths, because everything contains optical brightener. Now, every soap powder contains optical brightness, even the ones which are supposed to be for colours contain optical brighteners, because we're so used to seeing them now, we don't think white is white unless it contains optical brightener. And that's why everybody dancing in a nightclub glows in the dark, because of the UV light. It's nothing to do with the drugs they've been taking. Okay, coherent waves. What's a coherent wave? It's a wave which has the same frequency as in phase with each other, or has a constant phase difference. So the top two, number 1 and number 2, are coherent because they're in phase and have the same frequency. 3 is coherent because it has a constant phase difference. Okay, now that phase difference can be anything from 180 degrees, i.e. completely different, trough meets peak, to some variation of the difference, some angle, as in number 4. But for the memory of a definition, a coherent waves have the same frequency and are in phase. And if you have coherent waves, you can have interference. Interference is simply when two waves which are coherent add together so that the wave at each point is the algebraic sum of the two waves. So if you have two negatives, they become a bigger negative. If you have two positives, they become a bigger positive. And if you have a positive and a negative, they can cancel each other out. So we have constructive, where they get to a bigger wave, and destructive, where they semi or completely cancel each other out. Completely cancel each other out is obviously possible, but highly unlikely. Now, this is the equation for the diffraction grating. And this is how we get it, basically. Here it is at the bottom. Basically, we have to imagine that there's a triangle and the two waves coming from holes near each other form the triangle, particularly the side opposite the angle. So here's the angle here, and the side opposite it is the wavelength, because the difference between the wave here at the top, this one, and the wave at the bottom, this one, is exactly one wavelength, because they're arriving at the same point down the bottom, which is the big spot, which we call on the screen n equals 1. Now, if it's not n equals 1 but n equals 2 it's arriving at, then the wavelength difference will be 2, which is why instead of wavelength, we write n wavelength. But the principle's the same. Essentially, you have a sine relationship. The sine of theta is equal to lambda, which is the opposite, over d, the distance between the different slits, and that gives us the sine is lambda over d. Now, this has come up occasionally. This diagram gets you most of the marks, derivation of the formula, etc. It's not really a derivation. You draw the diagram and then you write down it's a sine relationship, and that is enough. Where it's used is in the diffraction grating, which is this diagram. Now, the last time we drew the diagram, a lot of people missed out the X and the D, the capital D here. You have to put that in because that's how you work out the angle. You can't use the protractor. You have to use these two systems. Okay? Of course, you measure them on both sides. You measure the X's on both sides and come up with an angle theta 1 on both sides, on the left and the right. And you find the average. The reason you find the average between these two angles is because if the diffraction grating isn't exactly perpendicular, then the two angles will be different. But by finding the two and finding the average, you eliminate the need to worry about that. Moving on to polarization, which is where light, which is normally in its unpolarized form, oscillating in many angles as it comes towards you, many different planes, is reduced to only one plane of oscillation. So polarization is when an electromagnetic wave or a transverse wave is reduced to just one plane of oscillation. Now, sound, being a longitudinal wave, cannot be polarized. Again, as I said, that's the definition between the two. Standing waves. Now, the main thing about standing waves is that they are, or stationary waves as they're sometimes called, they're two coherent waves of the same amplitude travelling in opposite directions meet. That's how they're formed. Their definition, the definition which I don't seem to have on this thing, is there's no transfer of energy, or no movement of energy. No transfer of energy. That's the definition. That's what a standing wave is. The two coherent waves meeting is how they're formed. And quite often you get asked both things. What is it and how is it formed? So what is it is a wave where there's no transfer of energy. How is it formed? Two waves travelling in opposite directions. There's a node where there's a minimum amount of vibration and an antinode where there's a maximum amount of vibration. But you have to remember that this is the wavelength between two nodes. That is one wavelength, because that is a normal wave. This is the wave. The other one is a representation of the other extreme. So that is our wave, and as you can see, that's from peak to peak. So that's our wavelength. Okay, then we have the standing waves mostly used in music, strings, closed tubes, open tubes. Here we have a stringed instrument, and so half of the length of the, twice the length of the string goes to wavelength. So 2 times the length of the string becomes the wavelength. Here we have the second one, the closed tube, that's something like a clarinet or an organ. This time we have 4 times the length goes to the wavelength. And back to open tubes, which are recorders, flutes, things like this. And again, 2 times the length of the tube is equal to the wavelength. And I'm afraid you just have to remember those. Then we have this experiment, which it's come up a lot recently, but you can never rule anything out. So you've got basically a vibrating tuning fork. You have to put in the word vibrating, which has been struck on the table and held over the top of the tube. And you move the tube up and down from zero, i.e. from being immersed in the water, until you get a loud sound, which is resonance. But you have to say loud sound. You can't just say until you get resonance, because that's not the experiment. That's not how you do the experiment. What you're looking for in the experiment is the loud sound. When you get the loud sound, you measure the distance from the liquid surface, the water surface, to the top of the tube. But you also have to remember to measure the diameter of the tube, because that's used in this section here as the end correction. That's because, as you can see in the diagram, the antinode is slightly above the antinode, which is the top of that wave, is above the top of the tube. And the amount it's above the tube is simply given by the diameter times 0.3, and it's a good end correction. It's called an empirical formula because it comes from experiment. Then we have to think about harmonics, which is multiples of the fundamental frequency, which happen at the same time. So you pluck a string, it produces the fundamental, but it also produces harmonics, which makes it sound like a guitar. Different quantities of harmonics make different instruments sound differently. They're always absolute multiples. So if you start with 100, the next one's always 200, the one after that 300. That's true in strings. Not so true in closed tubes because of the way it works. In a closed tube, you only have odd multiples. So it starts with 1, then you have 3 and 5. You don't have 2 and 4. It's easier to draw than anything else, and we'll do that later. In a stretch string, we have the formula from the logbook. Here it is. So if you get asked the question, how is frequency related to length in a stretch string, you simply write down this formula and then write down this part of it. It's also, of course, what graph we plot in the experiment frequency against length. We plot frequency against 1 over length to get the straight line graph through the origin, which proves the theory. And again, if you have tension instead of length, its frequency is proportional to the square root of tension. And again, this is the graph we draw. These are quite easy questions. And if you get a following question, remember to use the slope thing. We'll be definitely doing this. But the slope of the graph, for instance, if we had the graph, the second one, of frequency against the square root of tension, then all of this would be the slope of this graph. The slope of this graph would be 1 over 2L square root of mu, where mu is the mass per unit length of the string. So you work out the slope, you set it equal to that. If you knew the length, you could find the mass per unit length. And if you had the mass per unit length, you could find the length. This is the experiments I'm talking about. This is the diagram I expected to draw. What's missing again? What have I forgotten? I've forgotten to put vibrating in again because I have used the wrong PowerPoint. I've used an older version. So there's vibrating tuning fork. You've got the length measured, the paper rider. How do you know that the length, that the string is of the same frequency of the tuning fork? The paper rider jumps off. That proves that the two are at the same frequency because they're resonating. The paper must be in the middle. It must be quite small. Obviously avoid Plancks, etc. Musical notes have three qualities or characteristics. Now, the characteristic of a musical note is not, oh, it's very nice. Characteristic of a music note, oh, I like music. No, it's a specific physics question. Characteristic has a specific physics meaning. It means pitch, loudness, and timbre or quality. We usually just write quality, but timbre is the proper word. So pitch is frequency. It's the frequency of the wave. Loudness is simply the amplitude of the wave, and quality is the number of overtones or harmonics present. But that's the characteristics. Learn, learn, learn. And we have resonance, and I've written about Barton's pendulum, though I only include this in case it's asked specifically. If you're asked for resonance, definition, transfer of energy between two objects with the same or very similar natural frequency. That's your definition. There it is right there. Remember that. But the example is going to be your stretch string with the tuning fork and the paper jumping off. That's an example of resonance. If you're remembering it for the experiment, use it for this as well. Doppler. Now, we're all familiar with Doppler. All familiar with Doppler. And the Doppler diagrams I'm getting are now much better. Doppler is the apparent change in frequency due to the motion of the observer or the source. What I've left off here rather stupidly, I've just realised, is the motion of the fire truck, which has to actually be in, believe it or not, mainly because he's looking for things to take marks off you with. You also have to say that the person at A experiences a higher frequency than the person at B. Also, the person at A may be shitting himself because, of course, the fire truck's running towards them. Oh, I don't know. Did I really say that? And I recorded it. Please don't play that to your parents. Okay, so sound is a wave as well, as proved by the Doppler effect on the previous slide. What proves that sound is a wave is interference. It proves light is a wave as well. Light is proved as a wave by the diffraction grating experiment. The spots on the screen are interference pattern of constructive and destructive interference. So if you get a question of anything on waves which involves destructive or constructive interference, you have to mention them. So a diffraction grating experiment would be a diffraction interference pattern, so an interference pattern of constructive and destructive interference projected onto a screen because the waves were coherent. In sound, we can generate coherent waves with simply a tuning fork. The two prongs of the tuning fork next to the guy's ear, they are producing coherent waves. They are both the same waves. As we twist the tuning fork near our ear, we hear it go loud and soft. This is an interference pattern of constructive and destructive interference because of two coherent waves. Therefore, this interference proves that sound is a wave, just like the dots on the screen in a diffraction grating experiment prove light is a wave. And this was done, the light one was first done by Thomas Young. Okay, now we get some really boring, a couple of really boring slides. Limits of audibility. This is what the human here can hear. It's upper and lower frequency. Limits, and S mean there's two of them, upper and lower. The upper frequency that anybody can hear is 20,000 hertz. That's what some of you probably can still hear. And the lowest is around 20 hertz. I, of course, am somewhere down here as a virtual geriatric and virus victim. Potential, I hope. The threshold of hearing, the absolute threshold of hearing, is the minimum sound level of a pure tone that the average ear with normal hearing can hear in a noise. It's what you can hear. It's how loud you have to before someone sings. It's like, everybody apparently did a survey about 10 years ago, and 80% of people thought that their partner was deaf. Now, as only 5% of the population are actually deaf, I think that's probably wrong. I think people just think they're deaf because they're being ignored. I think I'm deaf because you're not even listening to this, are you? You're not listening, are you? I did tack this on at the end a bit. This is X-rays again. Electrons jumping from the surface of a hot metal by thermionic emission, then be accelerated by a high voltage to smash into a tungsten target. The electrons, about 10% of them, excite electrons in the tungsten metal, which when it falls back to its original ground state, releases an electromagnetic wave or photon of a very high frequency, and there are X-rays. X-rays, as I probably have told you several hundred times, are penetrating, they fog film, and they're not affected by fields. These are the properties of X-rays. The uses are to image the inside of a body or to kill cancer, but the properties are that they are penetrating, they fog film, and they are not affected by fields. Okay, so photoelectric effect, genuinely part of waves. This is where you shine light onto the surface of a metal and electrons are produced. We usually say light of a suitable frequency is shone onto a metal and electrons are released. Actually, we don't say light, we say electromagnetic radiation. Electromagnetic radiation of a suitable frequency is shone into a metal and electrons are released. So, this is how you prove it. It's ionization in a proving ionization from a radioactive source, but it's also the same experiment is used to prove that the photoelectric effect exists. You shine UV light. UV light will liberate electrons from almost all metals. It will certainly work for zinc. You have a charged electroscope. As you shine the light on it, the electrons jump off. They're electrons jumping. I don't seem to have trouble with the E. There they are. That's an E. Finally, electrons jump off the cap, and this means that the leaf collapses. So you shine the light, the leaf collapses, and you proved that the photoelectric effect exists. Well, what is the definition? So, we define the photoelectric effect as electrons being ejected from the surface of a metal by incident electromagnetic radiation of a suitable frequency. You just have to remember that. And Einstein's explanation was rather simple. One electron gets hit by one photon. Every photon is a package of energy, and the size of the package is entirely due to its frequency. Higher frequency, bigger size of package. Lower frequency, smaller package. You can change the intensity of the light, you can get more packages, but you can only change the energy of each package by changing its frequency. If the frequency is too small and the package not having enough energy, then the electron may come some way to being liberated from the material, but not get out. Whereas, if the package is larger, the frequency is more suitable, as in ultraviolet, there's enough energy in each package to liberate the electrons. So every package that hits an electron will liberate it. Now, the energy of each photon is given by Planck's law, E equals hf, which is, of course, in the logbook. Here is the graph, which pretty much made Einstein. This is how he won his Nobel Prize in 1910. Here is the threshold frequency. That's electrons beginning to leave the metal. Before, in this section, they don't, because the frequency is too small. The minimum frequency which causes them to leave is called the threshold frequency. And when you multiply that by the Planck's constant to find the energy that this occurs at, this is the energy it occurs at, that energy, the minimum energy to release an electron, is called the work function. So you have an electron coming in. This is the incident electron here, HF. You have the work function. Now, somewhere up here, up on the graph, up the top there, the incident radiation is bigger than the threshold by quite a bit. So what happens is the remaining energy gets turned into kinetic energy. Everything left over gets turned into kinetic energy. Energy left over turned into kinetic. So anywhere up and down this graph, the energy will be more than is needed, and so the electron, as the frequency increases, will move away at a faster and faster speed. Whereas here, the electron is barely liberated and does not move away at any speed. There is just enough energy to get it out of the metal. And I think that's almost enough. So let's have a very, very quick refresh. Reflection, waves bouncing off a solid object. Echo, you all knew that, I didn't do that. Refraction, that's waves changing speed and direction due to the change in density of the medium. Frequency stays the same. People hear across lakes. I probably did that with you. It's when there's cold air near water. The water keeps the air near it colder, refracts the sound towards it, so you can talk to someone a very long way away on water or lakes because all the sound is refracted down into the person from above. Diffraction, the spreading, not bending, spreading of a wave around an obstacle. Better with long wavelengths, sound around corner, spreading around a slit. Interference, two coherent waves meet, they combine at any point is the algebraic sum of the two waves. The main use of interference is to prove that things are waves. So you prove that sound and light are waves with experiments using constructive and destructive interference. Finally, polarization reduces transverse waves to one plane of oscillation. That's the best definition. That really is a good definition. Reduces transverse waves to one plane of oscillation. It's the difference between a transverse and the longitudinal. It's the difference between light and sound. And it's why we have to wear sunglasses when we're skiing, because snow polarizes the light, and when it's polarized, the glare is unbelievable and it can really blind you. Hope that's of some help. Questions to follow.